Alright, hello class. In this video we're going to be talking about concavity. So what concavity is about, it's basically what the second derivative tells us. If you think of the first derivative being increasing and decreasing and therefore being like velocity, concavity is the second derivative, which is essentially like the acceleration of the graph. Okay, so concavity is all about how or what the second derivative tells us. Okay, and a lot of how we analyze this is exactly like the first derivative test. You break things up into regions and you check to see whether the second derivative is positive or negative, and that's going to tell you what's going on with the original function. I mean, it's almost exactly the same, except you are looking at the second derivative instead. All right, so let's go ahead and define what concavity is and talk about how we analyze it. All right, so here's the strict, most basic definition of concavity. Basically, we say that f of x is concave up on an interval if its derivative is increasing on that interval. Okay, so concave up, f prime increasing. Okay. Similarly, f of x is concave down on an interval if its derivative is decreasing on that interval. So f is concave down if f prime is decreasing. All right, now what exactly does this look like? Okay, and like before, we had critical points when the derivative changed sign. Is there a point where concavity changes? All right, let's take a look at just a graph I threw up here, and we're going to graph a bunch of tangent lines on it. Okay, so here's the graph, here's a bunch of tangent lines, and as we look at the slopes of the tangent lines as they go along, because remember, the slope of the tangent line is f prime. Here we have a very steep positive value, and now these are all positive, but they seem to be, if I had actually drawn them correctly, the slopes are getting less steep. They are decreasing. So we could say that this might be a slope of 9, slope of 5, 2, this looks close to 0, and then this could be something like -1, -2, -3, -4, etc. Okay? Maybe -5, I don't know. But overall, if this is our f prime here is decreasing, right? Because the slopes are going downwards. And then here, they start to increase again, because if this is like -4, this is -5, and actually this looks a little less steep. So let's say that that's -3 again. This is -2. We're here at 0. Then we're back at, say, 2, 3, 4, etc. So now the slopes are going back to increasing. Okay, so here is where the graph is concave down. Here is where the graph is concave up. So we're concave down up to about right here, and then we are concave up. All right, and this point where it switches is what we call an inflection point. Okay, I'll give that definition in a second, but basically anywhere concavity changes is an inflection point. Now, it may not be obvious by looking at this, but we have established a visual pattern for concavity. What we don't want to do, when I was first learning this, we were just told to just plot a bunch of tangent lines and see what's happening. There's a much faster way to tell just from a graph where it's concave up or concave down. And here's how I think is the best way to remember it. Concave up is a smile, while concave down is a frown. All right, so concave up is a smile. So it could either be like a full parabola or just half a smile. Right? It doesn't need to be the full smile, but if it's making a smile type shape, it's concave up, while concave down is a frown. Okay, so concave down is a frown, so again it could be the full parabola type shape or just half of a frown, right? It doesn't have to be the full thing, but that's essentially what concavity looks like, right? Informally. Also, some people think of concave up U as a U, right? Up for U, and then down is just the upside down U. Okay, so that's another way that some people think about concavity, is up as a U. I think concave up is a smile, concave down is a frown. Okay, then an inflection point, let me give that actual definition. Right, inflection point is where concavity changes. So if the concavity of a function changes from up to down or down to up, then it's an inflection point. Okay, so give a quick example here. Where the function is concave up, that's going to be where it makes a smiley face, right? So here's concave up, and then here's concave up. Now, the question is, well, where does it change, right? And that's a great question. And the answer is inflection points tend to happen when, at least if the graph is smooth, it tends to happen where the function itself looks like a line, where the tangent line lines up with the graph itself, right, where they look the same. And I'll show that on a graph a little later, but basically it's where the function looks linear. Okay, that's essentially where they happen. But then around in here, this is where the function is concave down because, well, it's frowning in these regions. Okay, and around in here, where I have it in purple, this is where we have inflection points. All right, because we go from concave down to concave up to concave down to concave up. Okay? Okay, so to show something a little more complicated, this graph, well, it starts off concave up, right, because it's making a smile. Now it has a critical point here, but that's a sharp turn. And note that it does not change. It's still concave up. It's still making a smile, and then here is a vertical tangent line, but we'll notice that it changes to concave down here. I'll use blue. Right? This is suddenly concave down. So here you'll notice that this is a vertical tangent line, but at right about where that vertical tangent line is where it's changing concavity. Right? So that right there is our inflection point. Okay? So, well, how do we find inflection points? How do we find where a function is concave up or concave down? And it turns out it works almost exactly the same way as it does with trying to find critical points, because we're trying to find where f prime is increasing or decreasing. Okay, so to find intervals where f is concave up or concave down, we're actually looking at intervals where f prime is increasing or decreasing. So we can actually apply the first derivative test to the first derivative, essentially, and get that, right? So in other words, and I'll say we can apply the first derivative test to f prime by actually looking at f double prime, okay? Because if f double prime is positive, right, that gives us that f prime itself is increasing. Okay, and if f prime is increasing, that means f is concave up, right? So it's making a smile. On the other hand, if f double prime is negative, that tells us that f prime is decreasing, which if f prime is decreasing, that means f is concave down. So it's making a frown. Okay? Then, if f double prime is 0, well, that means that f prime has a critical point there. All right? Meaning that f has a possible inflection point there. Okay, it might not, and this we can also worry about if f double prime is undefined as well. That might be something we would need to look at. Let's actually just look at some examples where we find the intervals of concavity, find inflection points, etc. All right, so let's just look at an example here. Let's identify the intervals on which the function is concave up or down, then locate the inflection point. So we're going to look at the function f of x equals 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. Okay, so when trying to find concavity, right, concavity is always f double prime, right? That's what we're going to be looking at. So we're going to find f prime, and then we'll find f double prime. So f prime of x, that's going to be 12x cubed minus 12x squared minus 12x plus 12. A lot of nice 12s there. But notice we're not looking for turning points. We're not looking for increasing, decreasing, critical points. We are just looking for inflection points and concavity. So we're going to skip this and go straight to f double prime. Right? So we're going to get 36x squared minus 24x minus 12, and there we go. Now we are going to be looking for essentially critical points of f prime, right? So critical points of f prime, which are possible inflection points. Okay, so to do this, well, notice this is a polynomial, so nothing is going to make this undefined, so we can just set this equal to 0 and solve. Okay, so to do that, I'm going to start by actually factoring out the 12, right? So when we factor out the 12, we'll be left with 3x squared minus 2x minus 1. And we should be able to factor this, but in fact, I think I want to. It'll be easier to plug things in. So using the AC method, we want factors of -3 that are going to sum up to be -2. So it just looks like -3 and 1. Okay, and remember, for the AC method, we don't just factor sort of blindly. We split this into -3x plus 1x minus 1. Okay, and so now we can factor this using grouping, right? So we can factor a 3x out of the first piece to get 3x times x minus 1, and we can just factor a 1 out of this to get an x minus 1. That might be a little redundant, but it does help us realize that now we can factor out the x minus 1, and we're left with 12 times 3x plus 1 times x minus 1. Okay, so now solving this equation isn't too bad. X is either going to be 1, or from here it looks like it would be -1/3. Okay, and the 12 isn't going to affect anything. Okay, so these are the possible inflection points. And we analyze them in the same way we did in the past. All right, we set up a number line. I'm going to put a negative 1/3 here. I'm going to put a 1 here. And we're going to check f double prime in each of these regions and see whether they are positive or negative. Okay? So here for negative 1/3, I'm going to pick a test value of, let's say, negative 1. For between negative 1/3 and 1, thankfully we could pick 0. And greater than 1, I'm just going to pick 2. Okay, it really doesn't matter. You just need something. Okay? So, f double prime of negative 1. Well, now that I have this completely factored version of it, well, notice the 12 is always going to be positive, so we could actually ignore that. That's always going to be positive. We plug in negative 1, that's going to be negative 3 plus 1 there, so that'll be negative 2. And then negative 1 here is going to give us, negative 1 here is going to give us another negative 2. So we have a 12 times a negative 2 times a negative 2. So positive, negative, negative, so this is positive here. Okay, so f prime positive means our f is concave up, meaning it's making a U-type shape. All right, now I maybe shouldn't have honed in on here, but when we plug in 0, okay, we're going to get 12 times, well, that's just going to be a 1, and that's going to be a negative 1. So it's positive, positive, negative, so the whole thing here is negative, which means the original function is concave down in this region, so it's making a frown. All right, then in the next region, I'll pick green, f double prime, when we plug in 2, well, we're going to get a 12 times, that'll be a 6 plus 1, which is a 7, so 12 times 7 times a 1. Right, so that's positive, 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 positive. So if f double prime is positive in this region, that means we are concave up, so we are making a smile. All right, so here we have the regions of concavity. Okay, so we have that f is concave up on negative infinity to negative 1/3 and 2 to infinity. That's, sorry, I messed that up. 1 to infinity. Sorry about that. 2 was our test point. 1 was our actual inflection point. I'm glad that happened because that's a really easy mistake to make. So I should probably box these in now. And then f is concave down on the remainder on negative 1/3 to 1. Okay, and so that means negative 1/3 and 1 are actually inflection points. Okay, and there we go. That's that example. As you can see, it follows in almost the same exact method as the first derivative test, finding intervals of increase or decrease, except we're using the second derivative instead. Okay, real quick, before we move on to the next example, I wanted to show the graph. So we can see here at 1, we have an inflection point, right, because it's going from concave down to concave up. We can see that pretty clearly there. And notice that's what happens at these leveling off points. So this is a critical point that's not a max or a min, it's just a little whoop. Okay, and that's an inflection point, it turns out. Then we see at, it was negative 1/3, we have where it changes from, where it changes concavity. So I've marked it here. And so notice if I were to take the tangent line at this point or at this point, you'll see that at that point the tangent line aligns, it looks like it aligns exactly with the graph. All right, so here if I put in the tangent line, you can see that the function itself completely aligns with the tangent line, right? It looks to cover it exactly, and if we zoom in a bit, we see it even better. Okay, and so that's essentially where inflection points are happening. And we can see it here as well. That has a horizontal tangent line, right? And so if we graph that and zoom in, we see that this leveling off point happens where the tangent line seems to line up with the function. Now it doesn't, it's just that's where it looks like it does. Okay, so that's what's going on graphically with these. Okay. All right, let's do another example. Let's say f of x is 1/12 x to the 4th minus 1/3 x cubed plus 1/12 x squared plus 10x minus 5. Okay, and same question. We want to find the concavity and the inflection points. So what we're going to do, of course, is take the first derivative. Okay, so when we bring the 4 down, that's going to cancel with the 12 and leave a 1/3. So I have a 1/3 x cubed minus, well, this is nice, the 3 and the 1/3 canceled, give us minus x squared. Same thing here, plus x plus 10. Okay, and we'll do another derivative here. So the second derivative, f double prime of x, well, again, the 3's will cancel here, so we'll get x squared minus 2x plus 1. Okay, so now we're going to set this equal to 0 and solve it. Now, another thing to note here, this is, again, a polynomial. Nothing's going to make this blow up or mess up. So we can just factor and solve. So we should be able to factor this, factors of 1 that sum up to -2. So it'll be x minus 1 times x minus 1. Or it's a nice simple x minus 1 all squared equals 0. Okay, so x equals 1 is the possible inflection point. All right, so we only have one possible inflection point here. So we're going to make our number line, and we're going to check f double prime and tell us what f is doing. So I'm going to use this x minus 1 all squared guy for our f double prime. All right, that will be probably the simplest thing to plug things into. And since we only have the one possible inflection point, we only need to check, let's say here at 0 and here at 2. All right, so f double prime of 0, well, that's not bad. That's going to be -1 all squared, so that's 1, so that's positive. Right, so this function is concave up. Right, f is going to be concave up, which is a smile. Okay, then let's check the next region. Okay, which is, I'll use pink here. I'm going to check f double prime of 2. Well, f double prime of 2, that's going to be 1 squared, which is 1, which is positive again. In fact, we could have chose 3 if you think that's a little funky, or we could have chosen -1. It doesn't matter. Notice we're squaring this. This is always going to be non-negative, right? So we'll get positive. That means f is concave up again. So f is going from concave up to concave up. That means 1 is not an inflection point. Okay? So what does this look like on a graph? Let's see what this looks like. And what you're going to find is it's acting like it wants to be an inflection point, but doesn't actually change concavity. All right, so here's the graph, and actually on a standard window like this, it's actually kind of tough to see what's going on. Okay, but if we sort of zoom out a little bit, what you start to see is that there's a part where the function starts to look linear, and that's right at 1, which is that possible inflection point we found. But notice it doesn't actually change concavity. So it gets linear for a little while, starts to line up with its tangent line, but it's concave up, right? So, so that is part of why we have to check and analyze, because just because the second derivative is equal to 0 does not automatically mean we have an inflection point. All right, let's do another example here. Let's find the concavity intervals and the inflection points of this function. F of x equals the natural log of 3x squared plus 1. Okay, so what we need to do is take the first derivative. All right, so that's going to be natural log of the stuff is the derivative of the stuff, so that'll be 6x over 3x squared plus 1. Okay, now we're going to find the second derivative. Oh, fun, fun, fun. This is going to be a quotient rule. So it will be the derivative of the top, which is 6, times the bottom left alone, which is 3x squared plus 1, minus the top left alone, times the derivative of the bottom, which is going to be 6x. Okay, and then it will be the denominator squared. All right, now, thankfully, the top is going to simplify quite a bit. We're going to get 18x squared plus 6 minus 36x squared all over 3x squared plus 1. Right, so we're going to get 6 minus 18 times x squared all over 3x squared plus 1. So this is our f double prime of x. Now, here's something to note. Normally, we would worry about the fact that we're dividing by x stuff, right, because this could be 0. However, this is always positive. The denominator is never going to be 0, right, because the 3x squared, if we try to set this equal to 0, we would get x squared is equal to negative 1/3, and that's never going to happen. Okay, so the denominator is always greater than 0. So this we can safely just set equal to 0 and only consider the numerator equal to 0 because the denominator will never be 0. Okay, so a lot of ways we could go about this. I'm just going to move that over to get 6 is equal to 18 times x squared and then divide by the 18 to get that x squared is equal to 6 over 18, which is 1/3. Okay, well, this isn't going to be very much fun because that means x is equal to plus or minus the square root of 1/3, or we could rewrite that as 1 over root 3. And I'm going to do the complex, or not the complex, I'm going to rationalize the denominator. So this will be plus or minus root 3 over 3. I don't know if that is actually going to make things easier. And then we're going to set up our intervals and see what we get. So I'm going to put negative root 3 over 3 here and positive root 3 over 3 here. Now, you might think that this looks really gross, right? How we've set this up. These are really gross numbers. However, our test values are between these regions. So like a test value in here could be 0. A test value here could be 1. And a test value here could be negative 1. So we don't have to plug such nasty things into our f double prime. We just need to plug in things around these nasty values. All right, so it's not as bad as it actually looks. All right, so we are going to test our f double prime here. And that's going to tell us what's going on with our f here. All right, so f double prime of negative 1. Well, that's going to be a 6 minus 18 on top. So that's going to be a negative on the numerator and a positive in the denominator always. So we have a negative over a positive. So let me write it like this. It's negative over positive. So this whole thing is going to be negative. So f is concave down in this region. All right, so it's frowning in this region. right? If we plug in 0, on the other hand, so f double prime of 0, well, that zeroes this negative 18x squared out, so we're going to get a 6 over this thing, right? So it's going to be 6 over a positive. So positive, positive, we have positive. Okay, so our function is going to be concave up in this region. And then finally, let me clear this out. Probably shouldn't, but f double prime of 1, same thing we got here actually. We'll get the same value. It's 6 minus 18, so that's going to be negative over a positive, which is negative. Okay, so we will be concave down there. All right, so f is concave up on negative root 3 over 3 to positive root 3 over 3, and concave down on negative infinity to negative root 3 over 3 and positive root 3 over 3 to infinity. So that means the two possible inflection points we found, plus or minus root 3 over 3, are actually inflection points. All right, so the last thing I want to talk about in this particular lesson is the fact that concavity can actually help us find extrema. Since if f prime of c is 0, right, that means we have a horizontal tangent line. At that point, if f is concave up there, like where c is, then that means it makes a u, right? So if f prime of c is 0 and f is concave up at c, that means at c we have a minimum. Similarly, if f is concave down at c but also has this f prime of c is 0, that means we have a max because we need a horizontal tangent line and to be concave down. Okay, so that's going to be a max. Okay, so this actually leads us to what the second derivative test says. Okay, so here's what the second derivative test says. It basically says that if f double prime is continuous on an open interval containing c, with f double prime of c equaling 0, then if f double prime of c is positive, well, f double prime of c positive, that means we are concave up, so we're making a u. So this means that f has a local max, or excuse me, a local min at c. Okay. On the other hand, if f double prime at c is negative, right, then f has a local max, because if f double prime is negative, that means we're concave down, means we're making a frown, and a frown gives us a max. Okay. And then, unfortunately, we have a problem with this test, and that's if f double prime of c is equal to 0, then the test is inconclusive. We have to use the first derivative test. And the reason for that is because, well, if f double prime is also equal to 0, it could be an inflection point, right? So you could actually have this happening, or this, or this. I mean, either could be happening here. Okay, so this test won't work if f double prime is also 0. Okay, now I find that a lot of students don't like to use the second derivative test. I'm going to do a couple examples to show why this second derivative test is actually really nice. However, I'm going to start by saying that some of the homeworks will specify which one they want you to use. I don't care, okay? If you're more comfortable with the first derivative test, do it. Use it. The second derivative test is advantageous in a lot of cases, though, because often, well, there are a couple things. One, when you take a second derivative, in a lot of cases, you've made the function easier to deal with. And two, you don't have to find test values. You just plug in the critical point. Okay, So I have this here, advantages of the second derivative test. F double prime is often simpler, and we don't have to find test values. We just plug in the critical points. Disadvantages, though, and I'm just putting one big disadvantage. It doesn't always work, right? It's kind of strict. It won't work for critical points that are undefined, right? It won't work in situations like this where we have a spike. While the first derivative test always works. However, in the cases where the second derivative test does work, it's faster, right? It's way faster in certain cases, but not always, okay? Often the first derivative test is what you want. Also, if you're already finding concavity, you're probably already finding the second derivative anyway, right? So that's another advantage. All right, I'm going to show some examples of how nice this can be. However, I do want to specify, you do not have to use the second derivative test in this class. Those of you going on to Calculus 3, you do and will need it there. So I just want to preface that because this is at a point where you should be good enough to do the homework for this lesson. I just want to show this for those of you who maybe want a quicker way to analyze critical points. That's what the rest of this lesson is going to be. Okay, so let's look at an example here. Let's use the second derivative test to find the local extrema of this function here. F of x is equal to x cubed minus 3x squared. Okay, so to start, we need to find the critical points. Okay, so to find the critical points, of course, we take the derivative, f prime of x, and we're going to get 3x squared minus 6x, right? And this is a polynomial, so we don't need to worry about undefined critical points. And if we had undefined critical points, we would not want to use the second derivative test anyway, right? So we're just going to set this equal to 0 and solve. So we can factor out our a3x to get x minus 2. Okay, so 3x times x minus 2 is equal to 0, so x is equal to 0 or 2. So these are the critical points. Now normally we would set up our number line and find test points, but with the second derivative test, here's what we do instead. We find f double prime. Now, I'm going to use, of course, this version before we factored. That way we just use power rules instead of product rule. But this is going to be 6x minus 6. And then we literally just plug the critical points in. All right, so no trying to find test points in the regions and potentially confusing ourselves. We literally plug in 0. And we'll get 0 minus 6, which is negative. Okay, now that means f double prime is negative, so f is concave down. That means we have a frown. That means x equals 0 is a max. Okay, then we just plug in 2. So f double prime of 2, that's going to be 12 minus 6. That's positive. So that tells us that f is concave up. So that's making a u. So that means x equals 2 is a minimum. All right. And there we go. Just like that. Okay. I do understand that this is kind of confusing though, because you would expect the f double prime negative to be a max and the positive to be a min. So the second derivative test is kind of squirrely in that sense. It kind of acts in the way that you would think is opposite, but if you just remember, this is telling you the concavity, and concave down is what gives us a max, and a concave up is what gives us a min. So it's a lot less work to find extrema this way. Okay, a lot less work. However, it's a little more advanced. It's a little more taxing on the mind. You do have to sort of know your concavity really well
to align these things. Right, and here's the graph in my software just to show you. We have a max at 0 and a min at 2. All right, so there we go. It actually does give us what it says it does. Now, I will say, this method is not always great, right? It's not always going to be the best thing you can use, but when you have just a polynomial, and you don't have to worry about undefined critical points, it is the quickest method. Okay, so let's look at another example to show that very thing.
All right, so let's do another example here. We'll use the second derivative test to find the local extrema of this function. I should say if possible. It's not always possible to use the second derivative test. So we'll start by finding the critical point, and I'll mention there's a typo there. That should be x cubed minus 3/2 x squared minus 36. So we'll find the critical points. Meaning we're going to start by finding f prime. So we'll have 3x squared. Thankfully, this 3/2 cancels with the 2 to give us 3x minus 36. Okay, so now I'm going to find the critical points, and I'm going to start by factoring out a 3. So we'll get x squared minus x minus 12. All right, and then this should factor. I want factors of negative 12 that sum up to be negative 1. I'm thinking that's x minus 4 times x plus 3. Multiply to give us negative 12, sum up to give us negative 1. And here I'll set it equal to 0. So my critical points are 4 and negative 3. Okay, so for the second derivative test, well, we need to find f double prime. So f double prime of x is, I'm going to use the non-factored version. So we're going to get 6x minus 3. Okay, now look at how much nicer this is to plug things into. This is usually what happens when you're in a situation where you can use the second derivative test. And now I'm just going to plug these values in. All right, so we'll plug in 4, and we are going to get, well, that'll be 24 minus 3, so that's definitely positive. Okay, so positive double or second derivative means that we are concave up, which means we have a u. A u is a minimum. So x equals 4 is a minimum. Okay, next up, we're going to plug in the negative 3 to give us, well, that's going to be negative 18 minus 3. That's negative. Okay, so that means our function is concave down. Means we have the frown, which means we have a maximum. Notice that I draw this every time, right? Because I will even make the mistake sometimes of just thinking, oh, positive, that means max. But I will write concave up, u, concave down, frown, just so it aligns, and just so I don't make that silly mistake, okay? But there we go. I mean, that is it. We have now determined our extrema. All right, now to show the main issue with the second derivative test, we have this example here. So f of x equals 1/4 x to the 4th minus 1/3 x cubed. So, of course, we'll find the critical points. So we'll take the derivative, and we'll get x cubed minus x squared. Okay. And to find the critical points here, again, we only need to set this equal to 0. We can factor out the x squared to get x squared times x minus 1. So x is 0 or 1. So those are the critical points. Okay, but if we want to use the second derivative test, we of course would find the second derivative, f double prime, which will be 3x squared minus 2x. and we would just plug these values in. So if we start with 1, 1 shouldn't be a problem, because when we plug in 1, we're going to get 3 minus 2, which will be positive. So this means that f is concave up, and so we're making a u, so this means that x equals 1 is a minimum. Here's where we run into the problem, though. F double prime of 0 is 0. The test is inconclusive. Okay, so that means we can't use this test, so we have to use the first derivative test on x equals 0. All right, but not all is lost. We already know that x equals 1 is a min, so we can actually use that to our advantage. All right, so if we set up our number line, and I'm going to put 0 here and 1 here, I already know 1 is a minimum. So I know that at 1, f, since it's a minimum, is going from decreasing to increasing. So I already know that between 0 and 1, that f prime is negative, and past 1, f prime is positive. So really, all we have to do is check, say, at -1 to complete our first derivative test for x equals 0. So as you can see, we've actually done, with the second derivative test, a lot of work for the one critical point we couldn't use it for anyway. So all we're going to do is check f prime at, let's say, -1. All right, so if we go back to see what our f prime was, that was x cubed minus x squared. So at -1, that will be -1 minus 1. So that's -2. So that's negative. So it looks like we are going from decreasing to decreasing. So that means that x equals 0 is neither a max or a min, right? It's probably an inflection point, okay? In fact, if we were to set f double prime equal to 0, right, we would get, when we factor out the x, 3x minus 2. So x equals 0 and x equals 2/3 are the possible inflection points. So this pretty much tells me that this is likely an inflection point. All right, and if we look at the graph, this is a great example of why calculus is really helpful, because if you're kind of zoomed out, this doesn't look like anything is happening. Okay, but if you zoom in and take a closer look at things, then you start to see, oh yes, we do have a minimum here at 1, and it's not actually a turning point here at 0. In fact, it's kind of hard to see what's going on here at 0. Okay, but it looks like it's an inflection point because we go concave down for just a little while. Right, just, it looks like, until about 2/3, right? So, there we go. I think that is definitely good enough for this particular lesson, and I will catch you all on the next one.